Okay. So it's a great pleasure to have a speaker of this colloquium, Marika Taylor, professor at the University of Birmingham. This colloquium addresses one of the key unresolved questions in the field of fundamental physics, the compatibility between general relativity and quantum theory. Indeed, current knowledge of fundamental interaction is based on two pillars, general relativity and the quantum field theory of the standard model of elementary particles. General relativity is based on the analysis of the causal world line of events in classical space-time described by a Lorentzian manifold, and the geometry of space-time coupled to matter is described by Einstein's field equation, and among them, some describes black holes. Quantum field theory, on the other side, borrows from quantum mechanics the probability structure of events and the preservation of the probability in time evolution, that is, its unitarity. Wheeler, who coined the name black hole, claimed that black holes are places where the Fourier marriage of Einstein's relativistic laws with quantum laws take place. Indeed, a first step in this direction by Hawking, considering quantum field theory in the presence of a black hole, showed that black holes are not really black, in the sense they emit a thermal radiation and therefore evaporate. But then all the information about the matter that fell inside the black hole seems, so to speak, to evaporate with him, violating unitarity of time evolution. Worse, it has been shown that this violation would occur when the black hole is still in classical in size. So we seem to be in a paradoxical situation. Either strong effects of quantum gravity are needed to describe large-scale dynamics of regions of the universe, potentially as large as our solar system, such as the interior of a supermassive black hole, or the time evolution is not unitary. Recently, however, some results obtained using holography have suggested that the situation is not so black. Recognized leading expert in these aspects of quantum gravity is the speaker of this colloquium, Marika Taylor. She studied and then received her PhD from the University of Cambridge, with a thesis supervised by Hawking, with whom she had a long collaboration. She was later a professor in Amsterdam and then in Southampton, where she became head of School of Mathematics. She is currently professor of mathematics and physics at the University of Birmingham. She is also vice president and head of the School of Engineering and Physical Science at that university. For her achievement in quantum gravity, she won the Minerva Prize, awarded by the Netherlands Organization for Scientific Research. Her research interests span string theory, quantum field theory, gravity, as well as physics-inspired artificial intelligence and geometric learning. She used the holographic principle to study the physical properties of condensed matter systems and especially black holes. Today, we'll therefore be our guide into the fascinating theory of the black hole information paradox. So, please.
So thank you very much. I think that was a perfect ChatGPT sort of summary of my entire talk, actually. So it was quite fun. You almost previewed everything I'm going to say. So I'll say the same, but just that little bit slower, I think, as we go through. So today I'm going to talk about the black hole information paradox. And I'm aware we've got a great mixture of people in the room. So throughout this colloquium, I'm going to keep to sort of quite simple sort of descriptions. I'm not going to go into technical details. I'm really happy if people want technical details afterwards, but I'm going to keep it really, really simple to extract the key points. So I want to start with the basics of what is a black hole. So it really comes from, in modern language, well, modern as in 20th century onwards, the notion that nothing can travel faster than the speed of light. And so when we learn in physics, about projectiles and throwing them up off the surface of the Earth, and we think about the escape velocity, we know that as you make the object more compact, more dense, you actually need to throw something harder for it to escape. And that leads you to the sort of sense that actually if you have to throw something so hard that to escape, it would need to exceed the speed of light. That's not possible in Einstein's theory of relativity, and so it will be forced back downwards. So, I mean, the one way to think of it is a black hole is simply an object for which nothing can escape the interior, because things can only move as fast as the speed of light, and even things moving at the speed of light, the strong gravity pulls the light back round. Now, the other piece of terminology we need, which is familiar for everyone who loves science fiction, because black holes come up everywhere, is the surface of no return. The surface of no return, so if you fall in there, you won't be able to get out again. If you're inside there, you can't get out. That's called the event horizon. So that, for me, is the basic principles of what a black hole is. Now, what's the history of black holes? This is a potted history, because I think there's a lot more history to them. But I always find it fascinating that people had ideas about black holes long before Maxwell's theory of electromagnetism, long before Einstein's theory of gravity. So in the late 18th century, and Laplace in the 1800s, so John Michel and Pierre-Simon Laplace, both of them postulated the idea that there could be stars for which the gravity was so strong that not even light could escape. Now, of course, without a fully fledged theory of electromagnetism, they couldn't actually make this very explicit, but they had this idea. And even going back earlier than that, there were ideas about, again, sort of stars whose force was so strong that nothing could get out. But the mathematical understanding, as touched on in the introduction, clearly came from Einstein's general theory of relativity. So once Einstein wrote down his equations in 1915, very shortly thereafter, there were found exact solutions of Einstein's equations, which had the property of a black hole. So this characteristic that I'm defining, that you have a region of the space-time from which not even light can escape. Now, for a long time, there were, I think, questions about whether black holes were mathematical solutions of Einstein's equations, or whether they were truly physical objects. And so that, there was a long history about thinking about, how could black holes actually form. We're not going to go into that there, that, many of you will know much more about that topic than me. But actually, in terms of where, they really became discovered, where we really had experimental evidence for them, it's as we jump forward into the latter part of the 20th century. And, astronomical observations became that much more precise. The developments of instruments through the 20th century was such that you could really map out much more precisely than you were able to do before. And then black holes were discovered essentially by the impact of these objects. So they were not showing up on your telescopes, your electromagnetic telescopes, whatever wavelength you were looking in, but you could infer that they were there because of the impact that they were having on their surroundings. So you could infer that there was something heavy there. You could infer using, actually, Einstein's equations were actually in some sense just Newtonian Kepler type physics. You could infer that there was something of a particular mass, a particular spin pulling on its surroundings. And so, Cygnus X1 is an example which was, really discovered in the 1970s. It was inferred, as you can see from the picture on the left-hand side, from the pull on the neighboring objects. So, the fact that there were really objects out there that looked very much like black holes, we've again known for about 50 years. I should say, fun fact that Stephen Hawking actually had a bet with Kip Thorne. Kip Thorne, recognized as one of the pioneers of gravitational waves. They had a bet about whether Cygnus was actually a black hole or not. And Stephen actually bet that it wasn't a black hole. And his logic about betting that was that actually, if it turned out that it wasn't a black hole, and he'd spent all his life sort of working on black holes for nothing, well, at least he'd won the bet, right? And Kip would have to pay up. They settled the bet in the late 90s. There was enough sort of evidence that this was really behaving like a black hole according to Einstein's theory. Now, jumping forward to more modern times, there are many other ways of understanding, and getting evidence for black holes. But before we do that, one way to sort of think about black holes in the context of Einstein's theory, so, as touched on again in the introduction, Einstein's theory of gravity is a geometric theory. The slogan is that, the energy and mass is actually causing an impact on space-time. An object like a star is effectively curving the space-time around it. You can think of it as sort of pulling down the space-time, and you can think of the gravitational potential associated with the sun from Newtonian theory as being associated with that dragging of space-time. And the more compact your object, the more you actually curve the space-time. So if we go to more exotic stars, such as white dwarfs, such as neutron stars, they have stronger gravity around them. They curve the space-time around them more. And that sense of visualization is sort of quite helpful in thinking about a black hole. So the picture on the right-hand side is visualizing for you a black hole. So it's actually something where, you know, in the throat of the black hole, it's really curving the space-time more. And actually, as you fall into the black hole, you can see that the picture on the right-hand side kind of captures some of the elements. So once you go past that surface of no return, if you fall in, you go past the event horizon, even if you sort of turn around and you can actually accelerate yourself to, you know, close to the speed of light, you won't be able to get out again. And similarly, if you send your light signals from behind that event horizon, the light signals, they won't be able to get back. They'll go up towards the event horizon and they'll bounce back down again. So, you know, black holes clearly have very strong gravitational pull on the space around them. Now, in terms of modern evidence for black holes, there are several different ways, and again, many in the audience may know more, you know, of the details of the experiments than I do. But just to give you a sense of those, because we're going to touch on it as we come towards the end. So I think if we'd said, you know, 30 or 40 years ago, well, we'll actually, you know, within a sort of a couple of decades, we'll start imaging black holes, people probably wouldn't have believed it. But now we have the Event Horizon Telescope. You know, the name is sort of, it's named after the fact that it's trying to get images of black hole showing the detail at the scale of the event horizon. So the Event Horizon Telescope is using essentially an array of telescopes to put together a large amount of data to image the large black holes that sit at the center of galaxies. Picture on the left is one of their images. It's not one of the most recent images. It gets sharper and sharper with each iteration, but that is imaging a large black hole. Now, you say, well, that's not quite black, right? There's a black dot in the center, but what's going wrong, what's going on in the colors around it? So the halo that you're seeing around the black hole is essentially being caused by all of the matter and radiation in the surrounding region being dragged towards the black hole, spinning around as it goes around the black hole. As it spins around, typically things ionize or emitting radiation, so it's being sort of, you know, pulled towards the black hole. It's effectively an accretion disk around the black hole. So if you can get close enough to a black hole, you do see a black dot in the center, but you will typically see, in whichever electromagnetic wavelength you're looking at, you will actually see the electromagnetic radiation associated with the accretion disk. And for those who've seen the movie Interstellar, and it's iconic picture, that's the iconic picture. This is what you're actually seeing. You're seeing the accretion disk. The reason that you get such a sort of a distorted, so it's not just like you know, the rings around a planet, is because something which is, you know, even if the accretion disk sits in a plane, the light which is coming from behind the black hole, the force of the strong gravity is actually sort of curving it, so you also see it as though it's a sort of a little ring as well. It sort of gives a halo all the way around. So modern evidence for black holes, we see things that look like Einstein's theories on the Event Horizon Telescope. And of course, we also nowadays see direct evidence in terms of gravitational waves. So if you smash black holes together, you will actually create gravitational waves. So gravitational waves, again, another prediction coming out of Einstein's theory over 100 years ago. So, you know, just as you get electromagnetic waves as an automatic consequence of Maxwell's equations for electromagnetism, so you can see gravitational waves emerging as solutions of Einstein's equations. If you smash sort of very dense objects together, you will create an enormous burst of gravitational waves. You'll get enough gravitational waves that you can actually observe them a long time later, as far away from where the event took place. So the famous event in 2015, that where LIGO made the first direct detection of gravitational waves, that came from a collision between two black holes. Those black holes were between 30 and 60 times as heavy as our sun. And we know, we can sort of work out from the redshifts and so on, that the collision took place 1.3 billion years ago. The reason that we can look back and see something from 1.3 billion years ago and still see a significant amplitude of waves is because when you actually smash those things together and form one black hole, the gravitational waves that are released have 3 times the entire energy of the sun, right? So an enormous amount of energy goes out in those gravitational waves. So the picture on the left is sort of showing you the shape of the signal that they saw, and it's sort of showing you a step just before they're actually starting to merge. So these days we have ways to sort of, start imaging black holes and start exploring, their properties. But, for all it's called the Event Horizon Telescope, it's not really quite true that it's imaging the event horizon. I see that that was a very nice title, and for those who are involved with it, I think it's a fantastic thing to get your proposal funded. It's a really good title to choose. But actually, of course, what they're imaging is really the region outside the event horizon. They're imaging the accretion disk around it. They're not actually getting right to the surface of the black hole itself. And so there's a question of, what does happen as you fall inside a black hole? So if your astronaut goes in here, this is, I should have credited it, this is an image from nature, so that's why it's got the beautiful colors and so on, and the astronaut looks as big as the black hole. It's not really to scale, but it's a nice sort of image. So what happens? So again, if you sort of, just follow this, and actually if you just look at, the behavior as you fall in along a geodesic, and you think about, something that's going ahead of you in a sort of shining light, and you think about what happens, what you typically see, sorry, I'll just move up a little bit. There we go. Well, maybe shrink it a little bit. There we go. What you typically see are quite strong Doppler shifts. So if there's something which is emitting your light, you're actually going to see it very distorted, and you're going to see it sort of switching in frequency. And then as you pass through, you see those strange shifts of your, other things that fall inside with you. But then you will actually start experiencing some very strong tidal forces. So you'll start to be sort of pulled very, very hard by the gravitational forces. So what is the picture according to Einstein's theory in a black hole? So this is switching, I guess, between different ways of visualizing a black hole. We talked of before the fact that the black hole was actually sort of really curving the space-time, and there was a sort of a deep throat associated with going into the black hole. There was a point of no return, which is the event horizon. And that's the same picture which is shown here on the left-hand side. Now we're showing the surface of the event horizon in orange. That's just for visualization. It's not, of course, orange in reality. So you're falling in, and then you go past that, and you're going into this throat region. So Einstein's theory would say, so if you just look at the solutions of Einstein's equations and you start calculating curvature, that somewhere within that black hole, behind the event horizon, the curvature of space-time becomes large. And because the curvature of space-time is becoming large, the tidal forces become very strong. So you're really sort of pulled and squeezed. Now, actually what Hawking and Penrose showed in the 60s is that Einstein's equations inevitably tell you that somewhere behind the black hole horizon, space-time becomes singular. In other words, when you start calculating things, you get infinity answers. Now, usually in physics, when you start getting singular answers, infinities, it tells you that your physical theory isn't quite right. Right? So whether that was, when people started trying to use classical physics to describe what was going on in an atom, or whether it's in other areas of physics, an infinity is a sign that there's something incomplete in your description. And the interpretation here is that what's going on is that Einstein's theory is invalid because you need to take into account quantum effects when you get to those kind of scales. So your curvature is such, the scale of space-time is such that actually, your quantum effects of gravity are non-negligible, and you need a quantum theory of gravity. So by the time you come to the end of the 1960s, so that was a period in which there were, of course, rapid developments in terms of astrophysical observations, but in parallel, a lot of work which was going on around the world around understanding the features of classical black holes. It was a period, in fact, where particular new solutions of Einstein's black hole solutions of Einstein's equations were discovered. So those were solutions which were spinning black holes. And people had proven a number of interesting things about them. So one of the things that they proved is that black holes seem to be very different from stellar objects. So already when I sort of started talking about the sun and white dwarfs and neutron stars, we said, well, there's many different kinds of stars, right? It's not enough to just tell me how massive something is and how much it's spinning. We really have to give you other information about it as well. So black holes, according to Einstein's theory, seem to have a rather interesting characteristic, which is that they seem to be unique. They can form in many different ways astrophysically, and I'll show you that in a moment. And yet, actually, if we ask about which solutions of Einstein's equations describe black holes, they are remarkably simple. In fact, you can write down a solution of Einstein's equations. I'm not going to write the metric here. For some of you will know it, and for those who don't know it, it probably won't add much. But the solution that you write down of Einstein's equations, you can describe it entirely in terms of how much mass the black hole has and how fast is it spinning around. So the great physicist Chandrasekhar talked about this in terms of black holes being the most perfect macroscopic objects that we seem to have in the universe, because the only elements you need in the construction are the concepts of space and time. You don't need other sort of phenomena. You don't need to have an equation of state. So, for example, different types of stars may have different equations of state. You need to know about the pressure and so on inside them. Now here, all we need to know is the mass and the spin. Now, that's inherently surprising for the following reason. And as we go through the talk, we will eventually start to resolve this. This is surprising because there are many mechanisms in which you might form black holes astrophysically. So we talked about black holes, two black holes colliding with each other and forming a single black hole. But you can also have two neutron stars colliding with each other and forming a black hole as an outcome. You can have a single star that collapses. Chandrasekhar showed that. So actually the single star, when it's run out of fuel, eventually, when it's burned all its nuclear fuel, there's no pressure to sort of counteract the force of gravity. It just collapses down and forms a black hole. And then there are other mechanisms of forming black holes as well. But the statement here is that actually, once you've formed a black hole, you might have some gamma ray bursts, but ultimately when it settles down, all you'll have is a black hole which is described by the so-called Kerr metric discovered by Roy Kerr. So a metric that is a description of space-time which only depends on how much mass and how much angular momentum you have. So that's the classical features of black holes. Now, we've already touched on the fact that there seems to be something quantum going on behind the horizon of black hole. Deep inside a black hole, there's a singularity where you seem to need quantum gravity. But you can say, well, that's very interesting from an abstract perspective, but perhaps we don't care too much about that because by definition, we can't actually see behind the event horizon. So, the physics that we see will all be dominated by classical physics, classical Einstein theory. So I think that would have been the mantra up to 1974. The mantra would have been, there's nothing quantum needed about black holes. Everything quantum behind the horizon. If you're just interested in the physics outside, you don't actually need anything but classical physics. But now, in 1974, Stephen Hawking's probably his most famous work was that he discovered that black holes actually do radiate particles once you take quantum physics effects into account. Now, what does that mean? So, does it mean that black holes aren't really black? So, if we talk about a star having emission, and now we say that a black hole actually sort of radiates as well, why is it that we haven't seen it before? How does that tally with this sort of experimental results on black holes? The point is that actually, if you look at the rate of emission, the rate of emission is very, very low. So, it's almost, when you've got a battery which is sort of, dying on your torch, effectively the bulb looks as though there's nothing happening, right? It looks dark, even though it might still be emitting sort of a small number of photons. So black hole horizons typically emit radiation at such a low level because it's suppressed by the sort of, the Planck constant, that they effectively still look black. And of course, it's because that is such a low rate of emission, it's not something that we expect to be able to detect experimentally, right? We'd have to do an experiment on something which would be well beyond human timescales in order to actually be able to capture Hawking radiation. So Hawking radiation, I should say, the calculation that Stephen Hawking did was a complex calculation. So he was combining quantum theory with general relativity. He was putting quantum field theory of fields in a background which had a black hole. So a complicated calculation, really combining the quantum physics of whichever fields he was considering and putting it in a sort of curved geometry of a black hole. But there's a kind of a heuristic way to sort of think about Hawking radiation. I should say it's not entirely satisfactory, no heuristic explanations are entirely satisfactory, but in some sense it does capture some of the essence of it. So one of the defining features in quantum field theory is that you have virtual quantum pairs appearing and disappearing continually. The vacuum is non-trivial, right? There are things happening all the time, and you need to take into account these virtual pairs. Now, the heuristic sort of way to think about Hawking radiation is as follows. Suppose you have such a pair pop up close to the event horizon, and actually, before they can annihilate again, one of the pair has fallen off into the black hole. If that happens and is actually not able to get out again, its pair can escape to infinity as a Hawking quantum. So that's a heuristic way. As I say, it's a complex phenomenon, and the heuristics don't capture all of it, but it gives you a sense of how this can happen. If that particle falls into a black hole, it effectively has a negative mass and reduces the mass of the black hole, and the surviving particle that goes out to infinity carries away positive energy and effectively reduces the mass and energy of the black hole. Now, when you have a temperature, you have a conjugate variable, you have a conjugate thing to this, which is an entropy. And in parallel with the discussions around black hole temperature, there were also discussions about black hole entropy, particularly from Jacob Bekenstein. And it turns out that as well as that intrinsic Hawking temperature, black holes have an intrinsic entropy. The intrinsic entropy is proportional to the horizon area. So this event horizon is playing an important role. So it's proportional to the horizon area. You can sort of say that you basically get 1 unit of entropy for every Planckian unit of area of a black hole. In the picture on the left-hand side, sort of changing visualization again. So we were previously visualizing the black hole as a sort of almost a surface as we went into a sort of a throat-like region. Here we're sort of thinking about the black hole as being inside that shell, and the event horizon is the sort of, the surface that goes around it. So we're sort of jumping a little bit from 2 and 3D visualizations here. So black holes have an intrinsic entropy proportional to the horizon area. As we go on a little later, I'll tell you how big that is. It's a really big number because they get 1 unit of entropy for every Planckian unit of area. And actually that means it's a really large amount of entropy. Now, black holes are also the most dense objects in nature. So the point here is that actually the gravitational force pulls matter in. It's an attractive force. It's never a repulsive force. It's an attractive force. And actually things collapse ultimately to form black holes. Black holes seem to be the most dense object in nature. And then the second law of thermodynamics would imply that black holes maximize the amount of entropy that you can have in a given volume of space-time. Okay, we'll keep coming back to this, and picking up these 3 points. But the 3 points here, that black hole entropy scales with the area of the horizon, the area of a surface, that they are dense objects, and that this means that they're the most dense things that you can have. And this says that the most amount of entropy that you can have in nature is by black holes. They maximize the entropy in a given volume. So typically in quantum field theory, entropy scales with volume, not with surface. So you can construct sort of situations, you can contrive situations where entropy scales with the surface area, but typically it will scale, and usually it will scale with the volume. So this is another unusual feature of black holes. So we're kind of collecting unusual or interesting features of black holes. Now let's sort of first, give the first posing of the information loss puzzle. So almost immediately after Hawking discovered Hawking radiation, he realized that there was going to be a fundamental question here. So the picture on the left-hand side, which I should say is actually Stephen's own picture from the talks he used to give. So information loss. You have a black hole. You throw things into the black hole. You throw your obsolete computers in particular into a black hole. The black hole sort of sits there, Now, slowly, 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 over a very long period of time, it radiates out Hawking particles. It loses its mass and it radiates away. And again, I emphasize that this takes a long time, billions of years, it radiates away. And so eventually that black hole radiates away into just a bath of heat. So here is the paradox. If in the end point all we have is just purely thermal radiation, totally thermal radiation, how can we trace back and know how the black hole was formed? Or in other words, how do we know, which computers that we threw in the black hole? I think the graphic on the left-hand side is quite interesting in terms of thinking about this. So we throw away our old computer, it's got information on its hard disk. Think about even just that information. You throw it in, somebody else throws their computer in. You evolve in time, all you end up with is just completely thermal radiation. How do you know what you actually, how do you know what was thrown in? How can we trace back in time? So Stephen termed this the information loss paradox, and it was certainly something that he, together with many others, but certainly he spent much of the rest of his working career thinking about this question. Now, I'm going to sort of, the left-hand side picture is a bit of a more technical one. It's sort of showing the sort of evolution in time of a black hole. But actually, the right-hand side is really just giving you a sort of a bit of a sharper sort of statement of it. So in a slightly sharper physics language, what's going on is the following. You take something which is initially a pure quantum state. So ultimately, I had it in a sort of, a kind of picture, a macroscopic picture on the previous slide in terms of computers being thrown in. But let's take it back to fundamental physics concepts. We had an initial pure quantum state, and then it collapses to form a black hole. The black hole has no particular hair. In other words, it's described just by its mass and its angular momentum. It evaporates into thermal radiation. Thermal radiation is described as a mixed quantum state. So you've gone from a pure quantum state to a mixed quantum state, and that would be a violation of unitarity. Now, a more modern formulation of this, which is I think been used really in the last decade, is a statement that not all of the following postulates can be true. So actually, we're going to have to give up one of the four postulates, which is shown here. So the first is that there is unitary evolution of physics. Physics is unitary. The second is that just describing physics in terms of quantum fields, just particle physics, standard model particle physics, is a valid description outside the event horizon. Yeah. The third is that black holes have an entropy which is given by the area of the black hole. And the fourth postulate is that something that falls into the black hole experiences no strong forces. So one of those four things should not be true. So for, I think, many decades, people said, well, they are wedded to the fact that physics should be unitary, and so there just had to be a loophole somewhere in Hawking's argument. Now the statement is, well, if you want to keep unitarity, so you really want to keep number one, you need to choose your favorite one of 2, 3, and 4 to actually say which one you think is actually you're going to drop. And all of these, I should say, would be considered to be very reasonable postulates. So depending on your particular sort of taste, you might at first pass be more willing to drop one than other. But all three of them seem very reasonable postulates and are things that people had, in a sense, taken for granted. Now let's talk a little bit about whether loss of unitarity matters. So a common question which is asked is well, is this just a funny sort of quantum thing, right? Can we just relax this and not worry about unitarity? So unitarity, which I think we would call, if we were using more colloquial language, determinism, is really fundamental in quantum mechanics. Absolutely, in quantum physics, there are some things you can't answer with certainty, so that's poor Schrodinger's cat who's sitting on the left-hand side where we won't know whether they're dead or alive. Absolutely, but quantum physics is still unitary. So physics at one time still uniquely determines physics at earlier and later time once you know the dynamics of a system. And so it really is going beyond standard quantum physics if you say that you don't have unitary evolution. So that would be, a really substantial saying that quantum gravity itself wasn't unitary. Now, why would people spend a lot of time thinking about it? So whenever there is a sort of a paradox like this, there is always a sense that there is something very interesting to find in physics. So if you go back again 100 years and you think about the early 1900s, all the questions that people had coming from atomic physics, all the sort of puzzles they had about the structure of an atom, why would the electrons not be pulled by the Coulomb force down into the protons, how could it possibly have a stable situation of the negatively charged electrons being so not pulled down into the nucleus. And of course the resolution there ultimately came from quantum physics. It came from quantum physics, it came from exclusion principles and so on. And so resolving that particular paradox of why the electrons and the protons in an atom were not sort of, just collapsing and attracting to each other, it involved a paradigm shift. And many have advocated over the years that the black hole information loss paradox signals the fact that we need a paradigm shift. It signals the fact that we need to do something fundamentally different to understand gravity at the quantum level. And that's, I think, why it's attracted people to think about it for such a long time. So now let's come to certainly my favorite way to resolve it, but I think it's fair to say pretty much a consensus within the community about what the resolution of this paradox involves. So that brings us to holography and quantum information. So take a step back and pick up the point I said before, that black holes seem to be behaving very unusually. So if we took the quantum fields in the standard model of particle physics, the quantum fields would usually have an entropy that scales extensively with a spatial volume. So the fact that black holes have an entropy that scales with area, and that within quantum gravity, these should be the most entropic objects that you can have, okay, it suggests that quantum gravity is really fundamentally different. It suggests that actually, entropy scales with the spatial area of the boundary of any region. It suggests that there is really something, it's qualitatively different to a quantum field theory describing the standard model. And so holography really, in a sense, takes that observation, or the conceptual point, and takes it one step further. Holography suggests that the entire dynamics of quantum gravity is such that you can describe it entirely in terms of a theory in one less spatial dimension. Now, to get your head around that is quite difficult, so I'm going to first make the statement of the holographic principle and then show some pictures. So these ideas really started floating around a bit over 30 years ago from Prof and Susskind. So they were motivated by black hole physics. They said black hole physics says that quantum gravity is fundamentally different. Quantum gravity should be describable in terms of essentially a quantum theory without gravity in one less dimension associated with a sort of a surface, a boundary around space-time. They wanted to sort of infer that from black holes. So what would that actually mean? So it would mean the following. So take that picture. So that is Isaac Newton sitting under a tree. He's got apples falling over his head. He's thinking about gravity. So that's symbolizing gravity. And what holography would imply is that the motion of Newton's apples would be captured in terms of something which encloses the whole region. So think that the surface area, that's two spatial dimensions. It should be captured as a flatland theory with no gravity. So you can kind of think of it always about the quantum theory as being associated with a boundary around your three spatial dimensional world. Another picture, so where else do we think about gravity? So we think about motion in our solar systems. So you think about here, the moon going around the Earth. We think about the gravity of that. The motion in our solar system should be described in terms of non-gravitational dynamics in two spatial dimensions. And again, you can sort of see, you can think about the shell which is around this. So you think about the quantum theory as living on that shell. So conceptually quite a hard thing to think about. Now, to make holography work, what we would need to do is to understand how you relate things that you compute or observe in gravity and the things that you would actually compute or observe in a non-gravitational quantum field theory. So there will be a dictionary of some kind. And you can see in this picture here, we've got a dictionary where we're trying to sort of relate things that we think of in gravity, whether that is the motion of planets or whether it's black holes, and we're trying to relate that to the kinds of things that we think of typically in particle physics or in condensed matter physics, where we might think about particles scattering off each other and so on. So Toft and Susskind had the lovely idea of holography, but they really had no precise proposal of what would be the description, the dual description, the description of the quantum theory that captures gravity. So they kind of, couldn't take it too far. Now, over the past couple of decades, what has actually moved on is that we have found ways to relate gravity to a quantum theory in one less dimension. And the best understood example is, and I'm going to sort of explain each of the bits in turn, so quantum gravity in a particular kind of space-time, and that's related to quantum fields in one less dimension, but which have a particular kind of symmetry. And this is a famous discovery by Juan Mardesener in 1997. So what kind of space-times are we thinking here? So the defining feature of these space-times is that they have constant negative curvature. So I should say these are not space-times like the space-time we live in, which is locally flat, which actually in cosmological scale seems to have positive curvature, not negative curvature. These are negative curvature space-times. Now, negative curvature space-times, you can think of spatial sections as being the hyperbolic plane, which was illustrated famously by Escher, and depending on your frame of mind and how tired you are, you might see devils and angels, or you might see both simultaneously. But the mathematical thing that it's illustrating here, each of those devils and angels has the same proper area. So actually, the negative curvature is such that if you look visually at the angels as they crowd towards the boundary here, they seem to be smaller, but actually each of them has the same proper area as the ones which are in the center. So it has constant negative curvature. Now, that's just a spatial section. You can think about the spatial sections evolving in time, and that then goes back to the image that I had before. So the field theory, the quantum theory, the space-time is on the left-hand side, time goes vertically, you've got spatial sections, and then the quantum theory is associated with the boundary. So it's like a cylinder, as I showed you before. And so the correspondence says that something that happens in the inside, the gravity that happens in the inside, is associated with something on the boundary that doesn't have gravity. So the space-time has to be just constant negative curvature near the boundary, but you can have all kinds of fun things happening in the inside. It can be quite dynamical, it might be highly quantum. And so in particular in this picture, which for some reason the artist tipped everything by 45 degrees just to look visually better, but it's the same picture as before. Sitting in the inside, you can have all kinds of gravitational effects. You could even have naked singularities as shown here. You could have black holes and all kinds of those things. You can have all those things. And the idea is that all those strong gravity things which are shown inside that cylinder are described by things which are happening on the boundary. But the boundary theory has no gravity. Now, the boundary theory, what are the defining features we have here? So the basic feature that we have of a conformal field theory is essentially that it is scale invariant. You can scale up time and space, and it's invariant. Conformal invariance is a beautiful sort of property because it constrains many of the features of the theory. So in particular, you can look how the entropy has to behave or how the energy has to behave. All of that is actually fixed in terms of, because you've got no scale in the theory, you can fix this on scaling grounds. So conformal field theories, again, because they've got such a beautiful underlying symmetry, they have many, many beautiful properties. They are studied in many contexts, in particular for quantum critical points, in the terms of phase transitions, but they are very beautiful examples of quantum field theories. Now, we're not going to go into, we just defined enough here to say we've got gravity with negative curvature, and we've got a quantum field theory with scaling symmetry. We're not going to use any more details than that because we're not going to go into those details here. But we're going to ask the question of, well, going back to black holes, how does that help us? So the picture on the left-hand side, you can barely see the little black dot, and that's, I think, a little bit deliberate. The black hole dot is in the middle of that shell. So the black hole is in the middle of the space-time. The black hole, we know it has a Hawking temperature. And you can say, well, okay, if we're going to describe the black hole in the quantum theory, which doesn't have gravity, how are we going to describe it? So the holographic dictionary says that that black hole, in terms of what's going on in the quantum theory, is a thermal state of Hawking temperature TH, right? So it's just a thermal state. And it's a rather conventional thermal state. So here's, I think, a slightly clearer picture of the same idea. So you see the black hole sitting in the middle of the space-time. The shell on the outside, again, is meant to represent where the two-dimensional description that has no gravity sits. So that black hole is described, and again, I'll get a little bit more precise. It's a thermal density matrix in a unitary quantum field theory. Okay? So it's described in a quantum theory with two spatial dimensions. A standard quantum field theory, sort of textbook quantum field theory, we describe it as a thermal density matrix. Now, we make that identification, and then we say, okay, so the black hole, we've said the black hole will decay by Hawking radiation. So can we actually work out whether, you know, if we set up and use the dictionary, can we see that corresponding emission, that corresponding decay in the quantum theory? And indeed you can. In fact, it was done even before the full sort of fleshed out holography was found. Now, why is this important for the black hole information problem? So we are describing the black hole. We describe it in gravity, and we think about its Hawking radiation. But now we're saying we can equivalently describe it in terms of a thermal density matrix in a unitary quantum field theory. We can follow through the calculation, and we can see that we're recovering all the features of the black hole. But by definition, because we're describing it with a unitary quantum field theory, we know that at that evolution, that information is not lost. Right? So this, in a sense, settles the question. It took Stephen Hawking a few years to kind of concede it, I think, publicly. But you know, he really did. You know, I think the community sort of flipped very soon after Moldesenner's work in '97 to say, hang on, this really does actually settle the information loss problem. The evolution of black holes is unitary. We can describe the black hole in terms of a thermal state in a quantum theory in one less dimension. That evolution is unitary. So although we set it up in a particular context, you know, there are many versions of holography. There are many different variants of holography. It suggests that black hole evolution will always be unitary. Now we're sort of heading towards, you know, the sort of, you know, the implications of this for black holes. So where does the entropy come from? So that's the other question you could say. And you say, well, actually, of course, the fact that we're describing the black hole as a mixed state, the mixed state in the quantum field theory, it's described as a density matrix. So the entropy that's associated with that density matrix is actually giving us and reproducing the black hole. Okay, so that was actually by fiat, it's automatically built into that identification. So if that's a mixed state, the natural question would be, if you just took one representative of the mixed, of the ensemble of states, of the thermal ensemble of states, if you took one representative, what would that representative mean? Or another question, another way of framing it is the following. Within the quantum field theory, we've got a particular thermal state, but we understand that ensemble of thermal states, we understand the microstates that set up that ensemble. Again, this is standard statistical physics, right? It's just standard physics that we understand really well. So we understand its entropy, we understand the ensemble, we understand the variance between the ensemble average and different states and so on. We know all of those things. The underlying question in gravity has always been, if a black hole has entropy, what are the microstates that we're actually counting? And so this throws that back down again and says, well, now, in holography, if we understand that the thermal state is actually the black hole, what is an individual microstate? And again, I'm going to do some pictures to sort of, you know, show what people think are happening. So holography in broader arguments suggests that if you just take an individual microstate, then essentially you get something that looks very much like the black hole, except when you get very, very close to the horizon. So it looks like the naive Einstein geometry, except when you get very, very close to the horizon. And if you got close to the horizon, there will be small differences, and the small differences characterize what each black hole microstate is doing. And this also fixes our other problem, because we said we were confused about why, when you formed a black hole, we seem to always get something which looked the same. So we said, even if whether you form a black hole by colliding neutron stars or from collapsing a star, you always seem to get the same thing for any given mass and angular momentum. Now what we're saying is that information about how that black hole was formed is going to be captured in some very detailed structure, but really down at the horizon level, and so detailed that we are nowhere near resolving this astrophysically observationally. Okay? So the way I've drawn the picture on the left-hand side is a little bit suggestive. So again, the sphere here is meant to be the surface of the black hole. And what we're saying is that deep at that surface, so outside that, the geometry is just the same as the geometry of a black hole, an Einstein geometry black hole. But actually at the surface of the black hole, just beneath it, there are very, very small differences. So this gives you another way of sort of thinking about what's going on in a black hole, which is that in some sense, that horizon surface, or just beneath that surface, is almost behaving like a giant hard disk. It's behaving like a giant hard disk in that if you throw something in, it will actually keep a memory of it on the hard disk. The hard disk itself has a memory of how it was formed. And there's one sort of quantum bit of information you can have for every Planckian unit of area. So the enormous entropy of a black hole comes from that fact that you have one qubit of information. If we take a black hole that has the same mass as our sun, the amount of information that we can store in it would be about 10 to the 50 of these laptops. So it would be the dream of Intel or Apple or something like that to use a black hole. So it's enormous. 10 to the 50 is absolutely enormous. Now, again, the object, something which falls into the black hole, the idea would be that it's effectively changing the state of the quantum hard disk. So we're remembering what goes into the black hole because essentially you're changing the quantum state of the system deep inside that black hole. So the history of the black hole is recorded. The picture on the left, which was drawn by an artist collaborator of mine, I really like because it's got a reminiscence of the scream, right, as the astronaut goes in. But actually it's also capturing, so something's falling in, but actually that imprint, they're sort of trying to capture the fact that it's actually being captured and recorded in quantum bits of information. And again, in terms of what comes out, the tiny non-thermal corrections to Hawking radiation are the thing that's going to, again, enable us to recover the entire black hole history. So if I threw my obsolete computer in, you threw your obsolete computer in principle, you would be able to recover the entire black hole history. Of course, just as, if you burn a piece of paper, physics is unitary, or physics and chemistry is unitary if you burn a piece of paper. That doesn't mean it's actually feasible in practice to reconstruct all of it, right? But in principle, the evolution is actually unitary. It's just not practicable to do the reconstruction. So things which fall in, you will record what falls in, and that will come out again. So the information loss paradox, this whole paradigm, this whole framework of saying that the information is sort of being captured close to the horizon. It's being captured by sort of tiny difference, individual microstates. They capture the history of the sort of black hole. It all hangs together and solves all of the puzzles that we had. Now, in recent times, over the last 10 years or so, people have taken this one step further and said, well, actually, if you really start thinking about black holes and the space-time around them as effectively acting as a quantum computer, then this is a great sort of forum for doing thought experiments in quantum computing. Now, that's interesting not just to people who are interested in black holes, because typically the methodology that people think about for quantum computing, people think about relatively small number of qubits. Of course, laboratory experiments, we're talking 10, 100, 1,000. This would actually, the thought experiments, we've talked about that, the sheer magnitude of the entropy, the sheer number of qubits involved. It's actually a really different framework to think about thought experiments in quantum computing. So it's quantum computing thought experiments which involve vast numbers of qubits. And people have tried to use this to give new insights into different kinds of quantum algorithms, how you might do error correction in quantum computing, and so on. So let me sort of conclude there and actually sort of pause it a bit to reflect on sort of the 3 points which are shown here. So Hawking radiation, discovered 50 years ago, really emphasized the fact that you couldn't ignore quantum effects in black holes. Before Hawking radiation, it was thought anything quantum would just not be visible to us outside the black hole. He kind of emphasized that we actually, there were quantum things which were actually going to become important because Hawking radiation allows things to come out of the black hole. It raised a paradox which led people to sort of think fundamentally about the nature of the black holes. Now, the paradox about losing the black hole history is resolved by the holographic principle. It's resolved by the fact that really quantum gravity is different. Quantum gravity fundamentally can be described in terms of a theory without gravity in one less dimension. And it manifests in the fact that if essentially the event horizon is playing an important role. It's a surface or a sort of, almost like a surface. And as things fall into the black hole, the event horizon is keeping track of those in terms of sort of tiny quantum impacts as things fall in. So the holographic framework allows us to resolve the information loss paradox, but of course it's far larger than that because, and as anticipated, solving the paradox really gave us a paradigm shift. It told us that quantizing gravity was really fundamentally different than quantizing the other forces. And then the third piece, that actually, as the viewer on the left-hand side is sort of seeing up, so that they are looking up, the black hole is the black dot in the center, and then the little nodes around it, you should think about those nodes as if it's a nodes of a quantum network, a quantum sort of a quantum hard disk. You can think of space-time near a black hole behaving like a quantum computer. Now let me jump back to the very beginning of the talk when I was talking about modern observations of black holes. So I said, the Event Horizon Telescope is still imaging things which are very much outside the event horizon. It's very much imaging the accretion disk around it. So we're not near the point yet. It will be a long time perhaps before we really get to actually, be sensitive enough to the real details at the, sufficiently close to the event horizon that we see this phenomenon. But even before we can actually see this observationally, we can actually do really interesting thought experiments which come from actually thinking of the structure of space-time near the black hole behaving like a quantum computer. And that in itself can be interesting for understanding quantum AI, quantum learning, quantum networks, and so on. So I don't think Hawking 50 years ago would ever have anticipated that this would have come back round to thinking about computing. Quantum computers, of course, proposed by Feynman really in the 1980s, so 50 years ago weren't even proposed. But actually the fact that it's come back round and connected to quantum computing is remarkable. Clearly there's a lot more to do. So I think the idea that the information loss paradox is resolved by holography is accepted, and the fact that that what's going on is that things are being captured at the horizon of the black hole, the details of black hole microstates. But in terms of working out the details of how that works, and for different kinds of black holes, a lot of those details still need to be sort of worked out in more detail. So lots more to do, but certainly a really interesting, an interesting area to work in. And I will stop there. Thank you.
Thank you very much for this very beautiful and clear talk. There are questions? Okay, maybe I start. Okay.
I'm wondering if the holography is the only possibility to try to solve the information paradox, or there are other mechanisms that can be invoked somehow.
Okay. So the question is around: is holography the only thing that can be invoked? So certainly there have been many things which are considered over the years, and people still explore those possibilities. And you know, they should absolutely keep exploring them. One should keep exploring until one has experimental sort of verification of things. I think holography remains the dominant paradigm because it solves everything simultaneously. So if we took a side jump into inflation in cosmology, you know, why does inflation survive as the dominant paradigm? Because actually it solves many of the pieces. There are still unresolved issues, but it's the thing that works best. But absolutely, people should still try other things. Now, one of the ideas that people have had over the years is something called remnants. So they say that there's a crystal of, as a black hole evaporates, it evaporates into something which actually is a sort of a remnant at the end. Some of the ideas that came out of the remnants, you can actually think of, you know, they're not completely independent from the holographic ideas. There are synergies and things. So, you know, they can keep exploring those. People who work in, say, loop quantum gravity ideas, they also have their own ideas about how it would work. But actually, again, many of them interface with and share features of holography. And again, until we have experimental verification, of course, you should push all kinds of ideas. Completely agree.
Questions?
So maybe I missed this point, but so you said that there's a list of points and one has to get rid of one of them. Okay, so this is not unitarity, clearly. So which one is it that we get rid to explain the black hole information paradox?
So thank you. That's a really good point. And let me just flip back really, really quickly to the side, and I'll be very explicit about it. There we go. So I would say it's actually really the second and the fourth which we're getting at, which is that we're saying that very, very close to the horizon, there are non-trivial quantum effects. And so the description of, and again, I have to get a little bit more technical, local quantum field theory being valid outside the event horizon, that's a little bit subtle. There are non-local things coming in. So to point 2, you have to put a bit of a footnote there. And point 4 is a little bit subtle. So generically, a typical infalling observer will indeed experience no strong forces because you would expect that because the curvature of the metric is small. However, an atypical observer can actually encounter sort of quantum behavior. So again, a bit of a footnote to that 4. So it's 2 and 4. It's saying that there are some subtle pockets of quantum non-locality, which gels with the fact actually that quantum gravity theories are typically, you know, they're non-local with its string theory. So it's 2 and 4, and so we keep 1 and 3. Yeah.
Thank you for your talk. Very interesting. I'm imagining an infalling observer that falls into the black hole with a qubit of information. So he has like a box with 1 qubit of information, and there is another observer outside the black hole. Okay, if an infalling observer goes towards the horizon, should see nothing that changes in his reference system. So he enters with the qubit also. So he and the qubit enter with no other forces, no particular effects inside the horizon. But one observer outside the black hole should see this information splitting and make like be trapped on the surface of the black hole for holography principle. I think because the basis is like the information stands on the horizon and no enters. But this is like a duplication of information, or there is something that I miss in this process? Thank you.
So thank you. I think the question, it relates to the fact that at some point I'm going back to being quite simplistic and sort of, you know, simplifying the picture. I think the statement would be that as soon as you go into the horizon, there are strong quantum effects. So really, when I say the information is hidden at the horizon, it's hidden just beneath it, okay? And so there is still some causal disconnect between that information and the things that sit outside it. So it's not a duplication. It's not that the information is left at the horizon and the observer keeps going. The statement is that the observer just gets a little bit beneath the horizon, but then is effectively experiences strong forces and is pulled into their, they're effectively pulled to pieces into quantum information, right? So they actually sort of get trapped there. It's not that they keep going and leave the information behind. So that's the main sort of technical point, I would say. And it's essentially just behind the horizon that happens. But ultimately, we're turning quite complicated mathematical descriptions now into a particular interpretation, right? And this caveat that I gave in the answer to the last question, you do need to be careful to specify the type of observer you have going in and the type of trajectory they're going in and the specific features of microstates and so on. But again, this generic feature, it's not that you have a duplication, you leave the information at the horizon and keep going. It's that actually you keep going a small distance and there's nowhere else to go, you just get torn to pieces. So in a sense, that whole region which is sort of hidden behind the horizon, there's not a region that you can keep moving. It's effectively, everything just sort of flattens out and it just becomes, the information gets sort of trapped just behind the horizon.
Okay, thank you.
So related to this question, can we say that close to the black hole, it actually, space-time actually behaves similar to the end of the universe, maybe?
So I think that's a great question. And if I had more time, there are very deep analogies between what's going on in black holes and the beginning, well, particularly the beginning of the universe where we had the Big Bang. So that was known back to Hawking and Penrose. They were simultaneously thinking about both of those things. In terms of what's happening here, absolutely what's happening inside the black hole is it's becoming highly quantum. It's very much analogous to what's happening at the beginning of the universe. End of the universe, I think the jury's still out on that one of whether, it's probably not a crunch that we come to at the end of the universe. It's expected to just be a long, slow death of the universe. But yeah.
Thank you for the beautiful talk. So talking about the black hole entropy, do you add like Bernstein-Hawking entropy or von Neumann entropy connected to a density matrix? So are these two the same thing or different thing connected maybe by a mathematical equality or inequality?
So I think that's another fantastic question, because what we're saying here, and I sort of slipped to use the phrase at some points, a duality, that we can either describe physics in terms of gravity, or we can describe it in terms of quantum theory without gravity, right? We can use one or other description. Now, your point is almost which is the more valid, which is the one which is right, or are they both usable? They are meant to be equivalent. Now, what happens in a duality is that for any particular question, it is usually, not always, but it is usually more easily described in one language than the other. So if I go back to my example of Newton sitting under the tree waiting for the apple to come, that's the thing we learn when we do gravity, right? Gravity falling down. If I try to describe you that in the quantum field theory, it has a description, but it's incredibly complicated. So that description in terms of the apple falling is the one that's natural. But both are, to some extent, equally valid. They are different ways of looking at the same problem. Dualities in physics don't just exist between gravity and quantum theory in one dimension. There are dualities between different types of quantum theories, for example, which Seiberg and Witten and others have very much explored over the last 30 years. So that sense of two different descriptions of a system, they are both equally valid, but typically for any particular question, one may find that one description is the one which is more tractable to actually do the computation and get the answers.
Thank you.
Thank you. So a question came to my mind. If the information is on the event horizon and it's described by a quantum field theory, does an observer that gets in touch with this information cause the wave function to collapse when he gets in touch with this, and maybe modifying the information?
So the latter part would certainly be true, right? So if you start communicating with it, you're actually going to change it. Now, in terms of the former piece, you know, actually setting up a wave function in a quantum field theory in this context where there's certain non-locality, the details of that are subtle, but the principle that actually if something starts trying to communicate with it, that it's actually going to impact on it, it's going to change the state, that's certainly true. So if we imagined a hypothetical setting where we were actually trying to sort of, you know, do experiments which really sort of probe this, we would have to take that into account. But I should be honest here, you know, before we start to doing the technical details of your question, we need to really get the setup that much, you know, we've got to completely pin down the details of the setup. And so some of these subtleties which were asked around the question about how do 2 and 4 fail, there are slightly different versions, you know, there are slightly different ideas being explored on that, and one would need to pin those down. Yeah. But again, the detail, the principle that something outside which is trying to detect or see what's happening, it's trying to probe it, you know, it's going to face, you know, the observer is going to face the fact that they are still, to all intensive purposes, causally disconnected, and also that as they try to sort of make probes, they will be disrupting the system in itself. That's definitely true.
Okay, thank you.
Hi, thank you so much for the talk. Maybe I have missed it, but what can we say about the locality in holographic principle? Do we still conserve it, or are we?
Okay. So locality, so the quantum field theory which is associated with the boundary is local. So you know, it's a really good analogy to think of it as the kind of quantum field theory that describes particle physics, right? That's that kind of quantum field theory. But then the question of how that reconstructs the behavior of gravity in space-time, that's when non-locality comes in. So it's still the case that, it would still be the case that, you know, gravity, we still have, you know, local behavior, but the quantum behavior of gravity would have certain non-locality. And again, that's sort of touched on in these points here, that there is some non-locality to just be recovering information from the black hole. There has to be some non-locality which relates to the inside and the outside of the black hole. So it's a subtle, the locality in gravity is a subtle point. Yeah.
Thank you so much.
Hi, thank you for your presentation. I've read in literature that at the end of a black hole's life, it's possible that they can leave behind stable remnants. And so I was wondering, presumably these remnants might still have information on them, but wouldn't necessarily be accessible anymore. And I was wondering if this information is technically lost or...
Thank you. Thank you. So I think that's actually linked to the question which was asked before, which is, are there other ideas about black holes? So as you said, remnants is an idea. It was an idea which was quite popular, I think, sort of 30 years ago. Now, what I haven't said in this talk is there's been, you know, quite a lot of work in quantum gravity theories about understanding black holes and understanding them in, say, in supersymmetric contexts, for example. Use supersymmetry as a tool. And in all of those contexts, we don't have remnants, right? There's not remnants. So remnants in that sense, we haven't found an explicit realization in quantum gravity theories. In holography, they also wouldn't tend to come out. So in that sense, it's still an interesting idea, and I would absolutely support people exploring these ideas, but actually trying to find a more explicit example where a remnant shows up and to understand its properties, that would be, I think, important. So it's something people think about, but it doesn't show up in these contexts, and it doesn't show up in all the contexts where we understand a lot about the individual microstates of the black holes and the behaviors and so on. So, yeah.
So I have two questions. The first one is about the spin. I'm wondering, does the black holes have spherical symmetry? And if it is that, how can we say that they are spinning? And it is maybe related with the quantum meaning of the spin. And the second question is on the temperature. For example, for stars, we know that they are radiating away energy from their inner nuclear reactions. So basing on that, we can measure their temperature. But for black holes, we've said that there are particles that create and annihilate close to the horizon. And if a particle can't escape the gravitational field of the black holes, the other one can escape, and we can measure that radiation. So it's, for me, a quite different notion of temperature, and how can we say that that radiation is the temperature of the black hole itself?
Okay, so let me take the first question, so about black hole and angular momentum. So I'm using, I think, here the words spin and angular momentum somewhat interchangeably. Most of this discussion, I'm really thinking about this in the context of classical gravity, so it's actually just a classical angular momentum. I'm using the words interchangeably because when I start mapping that over into a quantum state in a quantum field theory, it does really become a quantum spin. Okay. Now, in terms of are black holes spherical, so you can have spherical black holes and they have no spin. If they have spin, they're actually not spherical. They actually tend to be distorted. Astrophysically, black holes will have spin because or angular momentum because they are formed from environments in which they have angular momentum. So they typically will. They would typically be rotating around. The next point about the Hawking temperature. So actually, I think that's, in some sense, that's a difference between macroscopic and microscopic sort of points. And it's also about, thinking about, thermodynamics context. So the gas in the room, we're thinking, the gas in the room is made up of, many different particles, each of them moving. But actually, if you coarse-grained this and you describe it macroscopically, you characterize things in terms of pressure and temperature and so on. So the same would be true here. We've got individual quanta coming out, but actually we're sort of thinking about a bath with a very large number of quanta, and that's where we describe it in terms of properties like temperature and pressure and so on. So that's the thing that's similar. A star has an equation, a typical star would have an equation of state. When it has a temperature, it's not exactly black body, so it's not exactly a black body. The statement by Hawking is that black holes are exactly black bodies, so they're perfect black body. Now what we're saying is that actually there are very subtle corrections to a black body. So whereas a star is typically far away from being a black body, and if you look at its radiation, you can actually trace back, and people try to do that with neutron stars. They try and trace back and understand the equation of state governing the neutron star. Here, it would be very, very subtle collections. So to all intensive purposes, it looks like a black body. It's got a very slow emission rate, and that would could not be observed on human timescales. But the principles of it are the same, right? That actually each black hole would essentially have very, very subtle differences from being a black body.
Thank you.
Else?
Thank you very much. I wanted to ask if there is a way to fit de Sitter spacetime into these configurations, into the holographic principle and the discussion.
Thank you. That's a really great question. There has been a lot of work over the last couple of decades trying to understand spacetimes with no curvature, zero cosmological constant, and spacetimes with positive curvature, de Sitter, because our universe is de Sitter-like. I think it's fair to say that there's partial understanding, but it is not in the same level of detail as for negative curvature. So it's very much a work in progress. And there are some technical challenges and there are some conceptual challenges, but it's certainly a really important topic because this is our universe. So that the paradigm we describe with negative curvature and conformal field theory, it's very elegant, but we don't live in that kind of universe. Positive curvature is where we live. So.
Ask, you mentioned the microstate. Do one have an idea of this microstate, what could be?
So, I mean, so that's certainly something I've worked on quite a lot over the years. To all intensive purposes, until you get very, very close, really very, very close to the black hole, it just looks like the Einstein geometry. That's a very good description. So it's really as you go at the event horizon level that you see very, very small differences. Now, what I in my group and others have done is in special setups where you've got supersymmetry, really make that very, very precise, right? So we can really characterize what the difference is between the black hole and an individual microstate are. Now the question is, how do you do that without supersymmetry? What does it look like for a Kerr black hole? But I still think that, the basic principle, this is, for grant proposals, I shouldn't say it because I should say you can observe it, but it is not going to be observable anytime in the near future because the differences, the deviations from Einstein's theory are just so tiny until you get so close to the event horizon. It's so suppressed, you wouldn't see it.
I don't.
As you renounced to point 4 regarding the infalling observer, does he experience something like firewalls or something less drastic?
Okay, so thank you, and you're right that actually I could have mentioned the word firewalls here because this is why it was reformulated. I think the conclusion would be it's not firewalls that are being experienced. A typical infalling observer is still not going to experience strong forces. However, atypical observers will essentially almost, I think a good analogy would be, if you think about my picture in terms of a quantum hard disk, if they encounter a bunch of qubits, if they happen to be sort of localized and you send something in and you almost shoot it at that, it will experience strong forces. But generically, provided you stay away from that, you will actually still experience no strong forces until you've actually crossed through into the horizon. I mean, this can get quite technical quite quickly about why people didn't quite believe the firewall story and what went wrong with it. But generically, I think the consensus now would be you're not going to experience something, but if you actually just target if you send a sort of a very focused sort of observer in, then it can experience quite strong forces and drama.
Okay, so I don't think other questions. So we thank again for this very beautiful talk. Thank you very much.